All right, in this lecture we're going to finish our section 4.3 material on separable differential equations. And in this last part of our section we'll talk about some applications of separable equations, which we'll continue to discuss in our next few sections. But we'll introduce some applications here. Now the biggest application of differential equations is in mathematical modeling. So generally, a mathematical model is an equation or maybe some system of equations which can be used to describe some physical process. So we'll start considering some applications of separable equations in math modeling. And this first example that we will look at is what is typically called a tank mixing problem. And this is a pretty classic problem in either a Calculus 2 class or an introductory differential equations class. So let's consider the following. We have a tank which we're told initially contains 120 liters of pure water. And we have some mixture which contains 100 grams per liter of salt, which is entering the tank at a rate of 2 liters per minute. And within the tank, this solution is kept well mixed, and it is leaving the tank at the same rate at which the solution was being poured in. So a question of interest here would be, well, how much salt is in this tank at any given time, or what would the concentration of salt in the tank be at any given time? So all that we have in the problem statement is information about how rapidly solution is being poured into the tank, or how rapidly it's leaving our tank, along with the concentration of salt in this solution that's being poured into our tank. So if we want to solve for the amount of salt in the tank, we're going to make use of a differential equation. All we're told is information about the rate at which the amount of salt in the tank is changing. So we're given information about the derivative, or the rate of change of the salt content over time. So in part A of this problem, we are asked for an initial value problem which would describe this process. So we're supposed to set up a mathematical model describing this. So our first step in these sort of modeling problems is to introduce some notation. So for these problems, I usually ask myself, well, what is the quantity that I'm interested in? And in this case, I'm interested in the amount of salt in the tank after some amount of time has passed. So let me start by introducing notation for that quantity that I want. So I'm going to say, let's take y, which will be dependent on time, t, to be the mass. Here I'm going to be measuring mass in grams, since our concentration of salt in the mixture we're pouring in was given in grams per liter. So y of t will be the mass in grams of salt in the tank after t, where time has to be non-negative, minutes. And the reason I'm using minutes as my unit for time is that in the problem statement we were given some information about the rate at which solution is entering the tank, which was at a rate of 2 liters per minute. So once I have the quantity that I'm interested in, or I've given it a name, y of t, I'm given information about the rate at which that quantity is changing, or the derivative of y with respect to time. So for this problem, well, there's only two things that can happen to affect the salt content within our tank. We have solution which is being poured into the tank at a given rate. So I would have some positive rate at which salt is entering the tank, or an increase in the amount of salt. And then I would have salt which is leaving the tank as this solution flows out. So if salt is leaving the tank, that would correspond to a negative value for the derivative. So we would be subtracting the rate at which salt is leaving our tank to find this derivative, dy dt. So let's see if we can find it. Here, our derivative, dy dt, is given by the rate in. Now the rate at which solution is coming into the tank was at a rate of 2 liters per minute. And then let's ask ourselves, well, how much salt was in each of those liters that's coming in? So we were told in the problem that this mixture contains 100 grams per liter, and it's being poured in at the rate of 2 liters per minute. So we have our 2 liters coming in each minute, and each of those liters has 100 grams of salt in it. So this would be the value for our rate in. We're going to have 200 grams of salt coming into the tank per minute. Then we have to subtract the rate at which salt is leaving the tank. Now we're told the rate at which this solution leaves the tank is the same as the rate in, that is 2 liters per minute. And let's think about how much salt is in each of these liters that is leaving the tank. So at any given moment in time, we have y grams of salt in our tank. Recall that y of t was the mass of salt in our tank at any given time. So we have y grams, and we were told that this solution is kept well mixed. So those y grams of salt are divided equally among the 120 liters of fluid which are in the tank. Now, where did the 120 liters come from? Well, we were told this tank started with 120 liters of pure water, and if the rate at which we're pouring solution into the tank is the same as the rate at which solution is leaving this tank, that means that it will have a constant volume of 120 liters. So simplifying a little bit, we would have 200 minus 2y over 120, or y over 60, in units of grams per minute for salt coming into this tank. So we have a differential equation which describes the rate at which the salt content is changing in our tank, and we were asked for an initial value problem. So recall, an initial value problem is just the differential equation together with an initial condition. So let's think about our initial condition. We were told a tank initially contains 120 liters of pure water. So initially, that is at the moment that we begin this process at, say, time 0, we have no salt in this tank. It's containing pure water. So our initial condition would be that y of 0 is equal to 0 grams. Now, once we have this differential equation, in part B, we are asked to solve this initial value problem that we found in part A and determine the amount of salt in the tank after t minutes. So using the differential equation that we had in part A, well, we found the derivative of y with respect to t was given by 200 minus y over 60. Or, for simplicity, in the next part of the problem, I might factor out a 1 over 60 from this coefficient of y, and that would leave me with, 60 times 200, so 12,000 minus y, and I can see that this equation is separable. If I want to solve this equation, I could separate my variables as dy over 12,000 minus y is equal to 1 over 60 dt. And now integrating on both sides, on the left-hand side, I would have the negative natural log of absolute value 12,000 minus y, and that's equal to t over 60 plus c. And I want to try to solve explicitly for y here. So if I were to first multiply everything by a -1, I would have the positive natural log of absolute value 12,000 minus y is equal to -t over 60 plus c. Now, why not minus c? Well, c was an arbitrary constant, so whether I give it a positive sign or a negative sign, it doesn't matter. It's still an arbitrary constant. Now, to solve for y, we would next exponentiate both sides of this equation. So exponentiating, I would have 12,000 minus y is equal to c times e to the -t over 60. So recall when we exponentiate and use properties of exponentials that this e raised to the -t over 60 plus c is the same as an arbitrary constant c times e to the -t over 60. We explained that in our previous parts of this section. Now solving for y, we would have y as a function of t would be 12,000 minus c e to the -t over 60. Or if you prefer, because c is an arbitrary constant, you could take 12,000 plus c e to the -t over 60. It doesn't matter whether you give this constant a positive or a negative sign, because it's still just an arbitrary constant. So what I found here is an expression for y of t, the amount of salt in this tank at any given time, but I haven't satisfied the initial condition yet. This is just the general solution of that equation because it depends on this general constant c. Now recall the initial condition that we had from part A is that y of 0 had to be 0, since initially this tank contained pure water and no salt. So applying that initial condition, we would have y of 0 is equal to 12,000 minus c times e to the 0, which is 1. And we were told this has to equal to 0. So it follows that c is equal to 12,000. And so, substituting this value of c back into my general solution, I have y of t is given by 12,000 minus 12,000 e to the -t over 60. And recall here that this was being measured in grams. Y of t was the mass of salt in grams within this tank at any given time. Now, in the last part of this problem, we're asked how much salt is in the tank in the long run. So if we begin this process and allow a long period of time to pass, how much salt will be in the tank? So from our work in part B, we have an expression y of t for the amount of salt in the tank at any given time. So if we want the amount of salt in the tank in the long run, we're going to look at the limit of this function as time, t, goes on forever, as time approaches infinity. So here, our function that we found was 12,000 minus 12,000 e to the negative t over 60. And as t becomes infinitely large, this e raised to the negative t over 60 term will decay to 0, and we're left with 12,000 grams. So in the long run, we will end up with 12,000 grams of salt in this tank. Now, this part C of the problem allows us to sort of validate the model that we came up with in part A. So, for instance, we could ask the question, well, does what we've done here mathematically really give a reasonable representation of the amount of salt in the tank at a given time? So let's think about how we could use our answer from part C to validate this model and make sure that it makes physical sense. So we're told here that we have a tank which initially contains 120 liters of pure water. And over time, we're pouring in this concentration or this solution that has a concentration of 100 grams per liter of salt. And this solution is flowing out of the tank at some rate. So eventually, in the long run, after enough time has passed, there will only be this salt concentration left in the tank. Any of the pure water that we had will have been mixed with this salt concentration and flown out of our tank. So let's think about the amount of salt that we would be left with. We have a 120 liter tank, and the concentration of fluid after a long period of time would be 100 grams per liter. So taking the product of our 120 liters and 100 grams per liter, we get our 12,000 grams of salt that would be expected to be in the tank in the long run. So since that seems to make physical sense in relation to the problem, we suspect that our model is a good model and that we got the correct solution of this initial value problem. Now, in our last example for this section, we'll look at another mathematical model governed by Newton's law of cooling, which will be used to describe how rapidly an object is changing its temperature in a room that's held at a constant temperature. So for this problem, we're told Newton's law of cooling states that the temperature of an object changes at a rate which is proportional to the difference between its temperature and that of its surroundings. So that is the further or the larger difference that we have between our temperature of the object and the temperature of the room in which it's being heated or cooled off in, the more rapidly that object would change temperature. So let us suppose that a cup of coffee has a temperature of 200 degrees Fahrenheit when it's freshly poured, and we know that after 1 minute it has cooled to 190 degrees in a room that is held at 70 degrees Fahrenheit. So the question is to determine when this coffee would reach a temperature of 150 degrees. So as with our last problem, for problems involving mathematical modeling, we first want to introduce some notation for the quantity that we're interested in. And here, the quantity that we're interested in modeling is the temperature of this cup of coffee over time. So let me give that quantity a name. I'm going to let y, which will be dependent on time, so y as a function of time, will be the temperature measured in degrees Fahrenheit, since that's what all of the temperatures in the problem are measured in, of this coffee after time, t, which has to be non-negative, minutes have passed. And I'm using minutes since time was being measured in minutes in the problem statement. So what I'm given in the problem statement is a little bit of information. I have the initial temperature of the cup of coffee is 200 degrees, and after 1 minute it's cooled to 190. And I know what the temperature of the room is. So how can we go about finding this temperature from that information? Well, in the problem statement, we're told that Newton's law of cooling will govern the rate at which this cup of coffee is changing temperature. So let's write out what we know from Newton's law of cooling. So Newton's law of cooling says that the rate at which an object changes its temperature, so that is the derivative or the rate of change of the temperature function, is proportional to the difference between its temperature and that of its surroundings. Now, when we say that two things are proportional, mathematically that means that one of these quantities is a constant multiple of the other. So I'm going to take the rate of change to be some constant k times, let's see what we were proportional to. It said proportional to the difference between the object's temperature and that of its surroundings. So the object's temperature is what we were calling y, and we're taking the difference in the temperature of our object and that of its surroundings. Now, the room temperature in this problem was given to us as 70 degrees Fahrenheit. So we have the following differential equation describing the rate at which our coffee will cool. And we also have an initial condition. At time 0, that is the moment that we first poured this cup of coffee, the temperature was given by 200 degrees Fahrenheit. So we have an initial value problem here, and let's see if we can solve this to find the temperature at any given time. Now, using separation of variables, I could write this equation as dy over y minus 70 is equal to the constant k times dt. And then to eliminate the differentials, we can integrate on both sides. Now my antiderivative on the left-hand side will be the natural log of absolute value y minus 70. And that will be equal to, the antiderivative of a constant k with respect to t would be k times t. And then I can add an arbitrary constant of integration c. So to solve for y, I would first exponentiate on both sides. So we would have y minus 70 is equal to e to the kt plus c, which can be rewritten as some constant times e to the kt. So using the same argument that we had in the first part of this section and in our previous problem, we can rewrite that exponential of a sum as the product of the exponentials, and then e to an arbitrary constant is just some new arbitrary constant in front of the e to the kt term. So now, solving for y as a function of time, we would have 70 plus this constant times e to the kt power. Now what we need to find is the value of this arbitrary constant c that would satisfy our initial condition. And recall our initial condition here was that at the moment this coffee was poured, that is after 0 minutes have passed, we have a temperature of 200. So applying that condition, y at 0 would be given by 70 plus c times e to the 0, which is 1. So we have 70 plus c. And we were told that this value has to equal 200. So it follows that our constant C would be 130. And then taking that constant and substituting back into the general solution, we have the temperature at any time, y of t, would be given by 70 plus 130 e to the k t. Now, in the problem, we were asked what time, or at what time, will the temperature of this coffee be 150 degrees. So to find that, we would take this expression that we just found for the temperature and set it equal to 150 and solve for time. However, there's one value which is still unknown. It is this constant k, which is the constant of proportionality we had when we were setting up Newton's law of cooling. So in general, this constant depends on things like what the object that's being heated or being cooled is made out of. So we usually have to have some other piece of information aside from a single initial condition in order to solve for that constant. And in this problem, we are told also the temperature of this coffee after 1 minute. So we were given that 1 minute later, after this coffee was poured, it had cooled to 190 degrees. So let's make use of that second condition. So here, the temperature, y, after 1 minute, so at time t equals 1, would be equal to 70 plus 130 times e to the 1k. And we were told that this value was 190 degrees Fahrenheit. So we can now solve this equation for that constant k, and we would have 130 e to the k is equal to 190 minus 70, or 120, in which case e to the k is equal to 120 over 130, or 12 over 13. And so this constant k would be given by the natural log of 12 over 13. Now once I have that value of k, I can take it and substitute back into the equation for y, and we have the following. Y of t is given by 70 plus 130 times e raised to the k, which we found to be the natural log of 12/13 t. Now, once I have this expression for the temperature at any given time, I'm ready to find the time at which this temperature will have cooled to 150. So to do that, I would take my expression for the temperature that we just found, and set this equal to 150. Now to solve for t, I could first subtract 70 from both sides. And I would have 150 minus 70, which leaves me with 80. And then I can divide through by 130, which would give me e to the natural log of 12/13 t is 80 over 130, or 8 over 13. And then taking the natural log of both sides, I would have the natural log of 12/13 times t is equal to the natural log of 8/13. And solving for t, we would have the natural log of 8/13 divided by the natural log of 12/13, where time was being measured in minutes. Now, of course, for practical problems, such as this one, if we were asked for a time at which our coffee is cooled to a certain temperature, we would not want to give our answer in this form. We wouldn't say, well, after natural log of 8/13 over natural log of 12/13 minutes, but we might use a calculator to approximate this value to the nearest minute. And we find that this is approximately after 6 minutes. So here, if we were looking for an exact value, we would give the following expression, or if we want a more reasonable answer, say rounded to the nearest minute, we could make use of a calculator, and we find that this is approximately 6 minutes.